Hello out there. I'm Joseph Aya from the University of North Texas, and I'm going to talk about what are n functions and why are they interesting. So first, to talk about n functions, we need to talk about what it means for a set to be a set of measure 0. So basically, it means you can cover your set by a union of open intervals, and the sum of those intervals you can make as small as you like. So, for example, just a set with one point in it is a set of measure 0, and then more generally, it turns out that any countable set is a set of measure 0. Something which is not a set of measure 0 is an interval where A is strictly less than B. But if you're familiar with the Cantor set turns out to be a set of measure 0. The Cantor set is made by taking the unit interval and then first removing the interval from 1/3 to 2/3, and then removing the interval from the middle thirds of what remains. So 1/9 to 2/9, and 7/9 to 8/9, and then you just keep this process going forever. Anyway, the Cantor set is what's left after you do all of this removing. And it turns out that the Cantor set turns out to be a set of measure 0. Okay, so what is an n function? Well, an n function is a function that maps sets of measure 0 to sets of measure 0. So in other words, they take small sets basically to small sets. Now, it turns out that that happens sometimes, but not all the time. So the most probably well-known example is if you have an absolutely continuous function. So then this turns out to be an n function. Anyway, it's one of the standard theorems that's proved in a measure theory course, and that is if you have an absolutely continuous function, it maps sets of measure 0 to sets of measure 0. Now, another sufficient condition for an n function is if the function is differentiable except on a countable set. Anyway, that turns out to also be an n function. Now, something which is not an n function is, along with the Cantor set, there's this function called the Cantor function. And basically, what it is, it looks like this. So normally, when you, on the first step of forming the Cantor set, you remove the interval from 1/3 to 2/3. So we define a function that's equal to 1/2 on that whole interval. And then you go over here to the interval 1/9 to 2/9. And on that whole interval, you define the function to be 1/4. And similarly, on 7/9, 8/9, you define the function to be 3/4. Anyway, you continue this process, and what you end up getting at the end is a nice continuous increasing function that maps the interval 0/1 to the interval 0/1. Now, it turns out, though, that it actually maps the Cantor set, this small set of measure 0, onto the interval 0/1. So the Cantor function maps the Cantor set, which is of measure 0, onto a set which has measure 1. And so therefore, this Cantor function turns out to be not an n function. Okay, so now what else is interesting about n functions? Well, here's an interesting property that n functions have. If you have a measurable function that maps measurable sets to measurable sets, then in fact that must be an n function. So what's kind of interesting about this is that this says something about measurable sets. So measurable sets don't always have measure 0, but it turns out that they have to map, if you have a function that maps measurable sets to measurable sets, then in fact it must be an n function. And so here's a way to prove that. You suppose that it's not true that there's a set of measure 0 such that f of t is not of measure 0. So I kind of drew a little picture here. I mean, these were all in just R1, but if you kind of think of it this way, f maps this tiny set to this big set over here. Now, we're assuming that f maps measurable sets to measurable sets, so this f of t is a measurable set. Now, there's a well-known theorem from real analysis that says if you have a set of positive measure, that you can always find a non-measurable subset of that set. So I denoted it here as S. Okay, so then if you pull back this set S and intersect it with T, you would get a subset of T, but T was a set of measure 0, so this will also be a set of measure 0. And now F has to map this set of measure 0 onto this set S, which was non-measurable. So anyway, so assuming that F maps measurable sets to measurable sets, then it's not possible for F to map a set of measure 0 to a set with positive measure. It must map a set of measure 0 to a set of measure 0. So that's kind of an interesting feature, if a function takes measurable functions to measurable functions, then it's in fact an n function. And the converse also turns out to be true. So if you have a measurable function that's an n function, then it must map measurable sets to measurable sets. So to me, this is kind of interesting because just knowing that it's an n function, well, that we only know how it behaves on sets of measure 0. But this says something, it seems, which is a lot stronger, that it maps measurable sets to measurable sets. Okay, so let's see how this goes. So suppose we have F, the subset of AB, with F measurable. Now, there's a famous theorem called Lucin's theorem that says that if our function here is measurable, that it turns out that it's nearly continuous. This famous theorem called Lucin's theorem says that f is continuous on some closed set, C sub n, and the difference between f and C sub n is a very small set. So you do this for every n, and you take up an appropriate union of these sets, and then you get this set T, which is f minus the union of these fn's. Anyway, this set is going to be of measure 0, and so that means you can always write this measurable set as a countable union of closed and compact sets, union with a set of measure 0. So then, if you apply the mapping f to this union, then you get the union of the f of fn's, union f of t. Now, since f is an n function and t is of measure 0, f of t is going to have measure 0. But also, these fn's, remember, little f is continuous on each of these fn's. So f of fn, so a continuous function evaluated at a compact set, is another compact set. And it's known that compact sets are closed and all closed sets are measurable. So anyway, so this says that if f is an n function, then it maps measurable sets to measurable sets. So to me, that's kind of interesting because that's not always the case that functions will do that. But now we know from this theorem that f, an n function, will map measurable sets to measurable sets. Okay, so it turns out that there's an analogous theorem if f is continuous, that if you have a continuous function, it maps measurable sets to measurable sets if and only if f is an n function. So that's kind of an analogous theorem to the previous one. But here's this another interesting theorem about n functions. There's this famous Banach-Zariski theorem that says if f is absolutely continuous, if and only if it's continuous of bounded variation and an n function. So one direction is not so hard, and it kind of follows from stuff we've already mentioned. But if f is absolutely continuous, then it must be continuous. And it's also true that it's of bounded variation. And as we said earlier, quoting one of the first theorems that we mentioned, that an absolutely continuous function maps sets of measure 0 to sets of measure 0. So, in fact, f is an n function. Now, the converse is a little bit longer, so I won't maybe go through all of this, but you look at how f behaves on an interval contained in AB. So, assuming that f is of bounded variation, then it turns out to be differentiable almost everywhere, and so you can write this set as a union of two sets where f is differentiable on all of B and A is a set of measure 0. Also, by the assumption that f's of bounded variation, this integral will be finite, the integral of f prime. So anyway, so then there's another theorem from measure theory which says that, so f of b here, the measure of f of b is less than or equal to the integral of f prime over b. So using that result, then the measure of this interval right here, so this f is continuous, so this is a nice compact set, and so f of bj minus f of aj is going to be less than or equal to this, and then by this result from measure theory we get this inequality. And so taking sums, then you get this, and since the integral of f prime over the entire interval is finite, then it turns out that if these aj, bj sets are very small, then this difference can also be made very small. And that's basically the definition of what it means to be absolutely continuous. So anyway, so thank you for listening. These results can mostly be found in Stromberg's book called Real Analysis. It's actually in the exercises section of this text. Anyway, I worked on this with a graduate student recently when we needed to come up with some topic for him to work on. But thank you, and I'll leave time for questions. Thanks.